3, 2, 1. Alright. So, as promised in our previous video, here in this next video for Math 2070 online only, we will talk about the matrix of a linear transform. Okay. So last time we set up what the idea of a linear transform is. It's a specific kind of mapping from Rn to Rm, respecting the fundamental operations of scaling and adding. In that video, we saw that matrices give rise to linear transforms, and now we're going to do the reverse. Linear transforms can only come from matrices. So let's do the following. Let's say I have a linear transformation from R2 to R3, and I have two pieces of crucial information. I know that T of 1, 0 maps to 1, 2, 3. And I know that T of 0, 1 maps to 4, 5, 6. And you already know the answer to the question that just appeared on the screen. Yes, it is. But why is that true? All right. Well, let's break it down. Given any element of R2, we know something special about the vectors 1, 0, and 0, 1. We call them the standard basis elements. And basis we'll make much more precise later on in the course, but we saw that the fundamental property these things have is that every element can be written as a linear combination of these. They're a spanning set. They are the spanning set. So X has to be this particular linear combo, and our mapping T is linear, and linear mappings respect scaling and adding, and linear combos are literally scalings and adding, so our mapping will treat it with respect. So if I look at T of X, I'll have T of x1, 1, 0 plus x2, 0, 1. T pulls out the scalars and breaks up the additions. And, oh, conveniently, I know precisely what these things are. I was told that this one is 1, 2, 3, and I was told this one is 4, 5, 6. And now I have a vector scaled plus a vector scaled, and as we discussed, that we define to be the matrix multiplication, where these form the columns, and this is the vector it's multiplying by. So there you have it, this linear mapping, where I knew where it sent the basis element 1, 0 and 0, 1. I was able to then take these outputs and make those the columns of our matrix. There we see, for this specific example, that if I do have a linear mapping and I have a little bit of knowledge of what it does to the standard basis elements, then I have to be able to find this matrix for it. And in fact, this maneuver always works. Indeed, if I give you a linear transformation from Rm to Rn, then the mapping has to be matrix multiplication, where the columns are precisely where the mapping sends the basis elements. That's it. No more, no less. And the good news with this is that I'm able to now create some pretty interesting linear mappings. Before we get to that, it's worth noting that A is usually referred to as the standard matrix for a linear transform. That makes it sound like there might be non-standard matrices, and probably because there are non-standard bases for Rm. That maybe we'll get into that a little bit later on, when we start changing between bases. Ooh. Alright. But let's talk about an interesting thing that we can now do with this. We now know how to create linear mappings. You just got to tell me where we send the standard basis element. That gives me the columns for our matrices. So it turns out that I can actually create a linear mapping that rotates things counterclockwise, or clockwise. In fact, as we will see here in a moment, rotation is in fact a linear thing in R2. Because if I know my mapping rotates things by pi over 4, if I want to find a standard matrix for this linear mapping, just rotate the standard basis elements by pi over 4. So here we think of 1, 0, that's the point on the x-axis. And if I rotate it by pi over 4, I'll pick up the root 2 over 2 and root 2 over 2. And I just think of the picking that point and rotating it by pi over 4. And similarly, the point 0, 1 on the y-axis rotated by pi over 4, we'll find ourselves in the second quadrant at a similar point, but the x-coordinate is now negative. And that gives me the matrix there. And in fact, there was nothing special about pi over 4 here. You can in fact figure this out for any possible angle, clockwise or counter, by using sines and cosines and drawing out the triangles. All right, now we don't need to go too crazy with that. I don't want to go too crazy with that, but sort of you can do it. All right, sweet. So we've now seen if you give me the standard basis elements where they go, I can create a matrix. And I now see that if I wanted to create an interesting linear mapping, I just got to think about where to send my 1, 0, and 0, 1. At least for R2. Obviously for R3, I need to figure out 1, 0, 0, 0, 1, 0, and 0, 0, 1. Cool. All right. Now, let's wrap things up by recasting some properties of functions that you may or may not have names for, and see how we can use matrices to solve questions involving these for linear mappings. All right, so a function from Rm to Rn is said to be onto if give me a element of the codomain, there is an element of the domain that hits it. Now, if our mapping was linear, that's the same thing as asking, hey, do the columns span Rn? Right, so that was one of the things we talked about a while ago, and we know that the columns of a matrix will span precisely when A has a pivot position in every row. In other words, if I row reduce, I don't have any rows of zeros. So for example, this mapping from R3 to R2, we know an echelon form of this is precisely this, and here we see we've got a pivot position in every row, and thus we're very happy. We now know that that matrix spans R2, and because it spans R2, that must mean this mapping is onto. Every possible element of R2 has an input that hits it. Quite nice. And a note here that's a little interesting because R3, we kind of think about it being bigger than R2. But if I want to hit everything in R2, if I have R3, you can kind of think about, well, just ignore the third coordinate and you're good to go. All right. Now, another property, now onto maybe one you encountered in your calculus life, but maybe not, but one you definitely did was the concept of one-to-one, which means that if my outputs line up, my inputs must be equal. So I pass the horizontal line test. Now, obviously, for things that are living in multi-dimensional worlds, it's a little harder to visualize the horizontal line test, but the principle remains the same. Now, a linear mapping, what happens when I know that two outputs line up? Well, then the output of their difference has to equal 0. So if I want a linear mapping to be 1-to-1, I need x and y to be equal. I know that x minus y always maps to 0. So if I have a linear mapping that only sends that only outputs 0 if I input 0, that would mean x minus y would have to equal 0, meaning that they're the same. And now if we remember, linear mappings are matrix multiplication. This is saying that a linear mapping is 1-to-1 precisely when ax equals 0 implies that x is 0, meaning the homogeneous solution system has exactly one solution, meaning that the columns are linearly independent. So all of those wonderful things that we talked about with matrices, knowing when their columns span by doing row operations, and knowing when their columns are linearly independent, which we can also get by row operations, we now see that you can recast those in terms of function properties. That's really cool. And makes for really fun homework problems. Oh boy. So, for example, on this one, let's consider the mapping from R2 to R2 defined as follows. Note that this has to be 1-to-1 because of this matrix right here, we can clearly see that this column is not a scalar multiple of that one. Right? If I scale this by 2, 3 times 2 is not 4, fortunately. So this mapping, note, I know immediately is 1-to-1 because the columns are linearly independent. I don't have to do any work. Pretty neat. And you can similarly show things fail to be 1-to-1 by noting that my columns are not linearly independent. And a really neat place this happens is if I have a linear mapping where the dimension of the domain is exceeding the dimension of the codomain. Note that it can't be 1-to-1 because the matrix associated with this would be an n by m matrix, and this is telling me that my number of columns outnumber my number of rows, meaning that in my echelon form, I'm not going to get enough pivot columns, so I will be forced to have free variables and thus have linearly dependent columns. So in particular, I just explained it. So the columns belong to that, and that must be linearly dependent. So in particular, and this is one of my favorites, so we just saw that there is a linear mapping from R3 to R2 that is onto, meaning that I can hit all my possible outputs. But obviously, when I looked at that, there was clearly inputs that are going to hit the same output. This particular fact that there is no one-to-one linear mapping from R3 to R2 is pretty neat. But I had one of my linear algebra professors, Professor Scott Fulton. He was a big fan of this result, and he was very excited in linear algebra class when he got to this because he then drew this picture on the board. And he drew it from memory. He didn't have a reference. If I was doing this in person, I would try to draw this, but I'd have this picture with me to try to draw because I can't draw this damn thing. So this thing, the impossible trident, is a visual object that, when you look at it, seems to have all sorts of interesting properties. Like, oh, look, there's 3 here, but over here there's kind of only 2, and it's tricking your eyes. Now, good old Professor Fulton, when he showed and explained to us that there is no one-to-one linear mapping from Rm to Rn, where m is bigger than n, right? And this can't happen because the columns would have to be dependent. So we can't have the one-to-one, meaning that there are multiple inputs going to the same output. He pointed out that this kind of explains pictures like this, because this picture lives in R2, and there was an object that was in R3 that you tried to put in R2, but because I can't do it one-to-one, I can't get every single point to go to only one point, I double up. And because I double or triple or quadruple or even infinitely many up, I'm going to lose information. So he made this big, bold claim that the reason two-dimensional illusions are possible is that I can't take things in R3 and linearly put them in R2 in a one-to-one fashion. So I always thought that was a really bold claim. He did follow it up with, like, I don't even know how to prove that, but I think this explains why you can draw these weird pictures in R2. And I always thought that was it's stuck with me for the past 20 years, I guess, at this point. And now I wanted to share it with you here at the end of this fun little video. All right. With that, I'm done talking about linear transforms for now. We'll see them a little bit later in the course, and they'll appear as we go throughout as well. See you in the next video.